Alright, so this first video is going to cover part 1 and part 2 of the notes, and it's an introduction to gases, how manometers work, and then some basic conversions involving pressure and temperature. The first thing we're going to discuss is a theory based on multiple experiments that attempts to describe the behavior of ideal gases called the kinetic-molecular theory. This theory states that gases are very, very tiny, and because they are so small, individually they do not have volumes. That's why they're able to take the volume of whatever container they're placed in. The individual gas molecules are constantly in motion, and they run into the container's walls in which they are placed. When they run into one another, they are not drawn towards one another, nor do they repel one another. So they don't act like magnets. They just keep bouncing around, more like balls on a pinball machine. And then the kinetic energy of our gas molecules is proportional to their Kelvin temperature. The warmer they are, the more kinetic energy they have. The cooler they are, the less kinetic energy they have. Pressure is force per unit area. A way to describe this, think about having your big toe stepped on with a pair of sneakers on, and then having the same person step on your big toe with a high heel shoe on. You're going to have a much smaller area with the high heel shoe, and so the overall pressure that your toe feels is going to be substantially increased compared to the sneaker. The same amount of force is being applied, so the only thing that's changing is the denominator of pressure. As that area gets smaller, the pressure would increase. A couple of devices that are used to measure pressure include barometers and manometers. You may hear barometric pressure mentioned on the Weather Channel or other weather programs from time to time. Barometers are used to measure the atmosphere's pressure. It was invented in 1643 by an Italian scientist named Torricelli. If you look at the picture to the right, basically as the air pressure interacts with that barometer, it's going to push the mercury level down, and the mercury level is going to rise based on what is the pressure of that of the air that's surrounding it. Manometers are able to measure the pressure of a gas that's in a container. It does this by looking at the difference between the gas's pressure and the atmosphere's pressure. The difference between those is what that delta H stands for, and that's the difference in the mercury levels from one side of the manometer to the other. Let's take a closer look at that. When the atmospheric pressure is more than the gas's pressure, this is like a seesaw, the atmospheric pressure is able to push the mercury level away from it, so the mercury level will be closer to the gas portion of the manometer. If the gas has a greater pressure, is able to exert a greater pressure than the atmosphere, the gas pushes the mercury level away, and the difference between the two will be that H value that's listed over there on the right-hand side. And again, the atmospheric pressure is the one that's open to the surroundings, and so that's the side where you see the arrow, the container isn't closed off. There's just an arrow pointing to the atmospheric portion. So let's do a couple of examples with these. On your homework, you could be asked to find the atmospheric pressure, which is what you're going to be asked in these two examples, or you could be asked to find the gas's pressure, or you could be asked to find the difference in the mercury levels between the two. So let's label for this first, for both of these examples, what's happening. Again, the open side is your atmosphere, the closed end is the gas pressure portion. And so we see that we have the mercury level pointing higher towards the gas side than to the atmospheric side. Because it's closer to the gas side of the manometer, that's telling us that the atmospheric pressure is pushing down on it and must be greater. So if we wanted to calculate what the atmospheric pressure is, we would need to take the gas's pressure and add to it the difference in the mercury levels, since we want the atmospheric pressure to be higher. So 664 when added to 98 would give us a pressure of 762 millimeters. If we apply that same logic to the manometer on the right, again the gas portion is the closed end, the atmospheric pressure is, or the atmospheric side is the open end. This time we see that the mercury level is closer to the atmosphere than to the gas, which means the gas is exerting a greater pressure than the atmosphere. And if we wanted to calculate the atmospheric pressure, we would need to subtract away that difference in mercury levels because we want the atmospheric pressure to be even smaller. So we would take 98 away from 854, and that would give us a difference of 756 millimeters. You're going to have examples like this on your first worksheet. I think it's entitled Manometers Worksheet. Second part that we're going to talk about involves conversions. We're going to look at some different units of pressure. You can have pressure measured in atmospheres. You can also have it measured in millimeters of mercury, and you can have it measured in the metric form, kilopascals or kPa. These three conversions are equal to one another. So 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is also equal to 101.325 kPas. And then 760 millimeters of mercury are the same as 101.325 kPas. So this is known as the pressure bridge, and we can use these three units of pressure to convert between any of the others. And you will need to know these three for any future quizzes. So our first conversion is going to take the pressure of steam that's at 1.5 atmospheres, and we're going to convert it to millimeters of mercury. So just like we've done every other time we've done a conversion, we start with what we're given, the 1.5 atmospheres. We want to set up our conversions so that the atmospheres get canceled out, and the millimeters of mercury are what we're trying to find, so they're put in the numerator. According to our pressure bridge, 1 always goes with atmospheres, 760 always goes with millimeters of mercury. The atmospheres cancel out, and we multiply across, divide by 1. And you would get 1100 millimeters of mercury. I think it was more like 1120. Don't hold me to it, but that's because of the sig figs with the 1.5 atmospheres that we round it to 1100. The relationship between atmospheres and millimeters of mercury is a defined value, so that will not affect our sig figs. And as we've done in class, you can always put that 1.5 atmospheres over 1. Sorry, I just forgot that, trying to make this up a little bit easier for you guys. Our second conversion is going to be taking the pressure in Breckenridge, Colorado. It's approximately 520 millimeters of mercury, and we're going to see what that's equivalent to in kilopascals or kPas. Just like we did with our first problem, we start with what we're given. Again, you could put that over 1. Sorry, I forgot. We want to get rid of the millimeters of mercury, so they need to go in the denominator. Kilopascals are what I'm trying to find, so they go in the numerator. Millimeters of mercury always gets 760. Kilopascals gets 101.325. This is the only pressure conversion pairing where you will have different numbers other than 1 in both the numerator and denominator of your conversion factor. The millimeters of mercury cancel out, so I multiply 520 by the 101.325 and then divide by 760. 2 sig figs due to the 520, so I round this to 69 kPa. I believe this is the second worksheet. You'll have conversions involving these three units of pressure. Finally, we're going to take a look at temperature scales. We're going to look at Fahrenheit, Celsius, and Kelvin. I did cross something out in your notes. It says for Fahrenheit it's used widely in the U.S. The other place that it will be used in is Britain, but I think you're more likely just to see it here in the U.S., so you can mark that part out of your notes. It's also used in the engineering field. And we see the degree sign because you can measure Fahrenheit temperatures. Celsius is used in Canada and throughout Europe. It's also found in the physical and life sciences. We see the degree C to represent Celsius. And then the scale that you may not have been as familiar with before chemistry class, the absolute Kelvin scale. This one is used in the sciences, but it is not measured. It is a calculated scale so that you can have no negative temperatures, and we'll see how to do that on the next page. And that's why there is no degree sign with the Kelvin in terms of its unit. So I gave you a couple of equations on your note sheet to go between Celsius and Kelvin and Celsius and Fahrenheit. The T's are just referring to temperatures. You may like these two equations a little bit better. If you do, you're welcome to write those down. They're representing the same thing that you already have on your paper. They just have, instead of T in parentheses degree C, they just have the Celsius plus 273 gives you Kelvin. The 1.8 times Celsius plus 32 gives you Fahrenheit. You are going to be expected to know how to go between Celsius and Kelvin. You need to know that equation. If I ask you to go between Celsius and Fahrenheit on a quiz, I would give you that equation. So the only one that you need to know is this one up here, being able to go between Celsius and Kelvin. I always remember this one, that Celsius is the third letter in the alphabet, K is the 11th. I think that's right. So Celsius is always smaller than Kelvin. Kelvin is always larger than Celsius. So we're going to do conversions between each of these scales. First one we're going to do is take a look at Celsius, and we're going to convert it to Kelvin and then to Fahrenheit. It says the average temperature in school is 25 degrees Celsius. So if we were going to go from Celsius to Kelvin, we would need to add 273 to that 25, and that would give us a temperature of 298 Kelvin. If we were going to go between Celsius and Fahrenheit, we would need to take that 25, multiply it by 1.8, and then add 32 to it. And when we do that, we would get that it has 77 degrees Fahrenheit. If you look at both temperatures, you started with temperatures that had no digits past the decimal, and whatever you have in your initial temperature, that's what I would like you to report in terms of decimal places in your final answer, which is why 298 had no decimal places and 77 had no decimal places. Our second example is going to be taking a Kelvin temperature and going to Celsius and then to Fahrenheit. We're always going to have to use Celsius to connect Kelvin to Fahrenheit, so let's find the Kelvin Celsius one first. To do that, this time we subtract 273 away from our Kelvin temperature, and that gives us a temperature value of 660. Notice I wanted to keep the ones place, which is why I put a decimal after the 0. If you left that off, that would not make points in terms of just having that number of decimal places. They're just trying to be consistent. As I said, we do need the Celsius temperature in order to go between Kelvin and Fahrenheit. So now that we have that Celsius temperature, we can just substitute that into the Fahrenheit to Celsius equation, and that'll give us what our temperature from Kelvin would be in Fahrenheit. Again, keeping that ones place significant, 1220 degrees Fahrenheit. Our last example is going to be taking Fahrenheit and going from Fahrenheit to Kelvin and then Fahrenheit to Celsius. Many meals are reheated at 350 degrees Fahrenheit. Again, we can't go straight from Fahrenheit to Kelvin, so let's use Fahrenheit and get Celsius first. And this is probably the trickiest one of the bunch because you have both an addition and you have a multiplication. So algebraically, we need to combine our constants, which means we need to subtract 32 from both sides. You don't need that equal sign in there, sorry. And when you subtract 32 from both sides, you get 318 is equal to 1.8 degrees Celsius. Now I can divide to isolate the degrees Celsius. And once I do that, it'll give me 177 degrees Celsius. At this point, I can now find the Kelvin by taking that 177 degrees Celsius and adding it to 273. That gives me 450 Kelvin. The last slide we're going to talk about is more of a definition that we're going to be using in future problems, and that's STP. We've seen this before. STP stands for standard temperature and pressure. If you are wanting a standard temperature, that's 0 degrees Celsius or 273 Kelvin, what its equivalent would be. And then standard pressure would be any of our pressure conversions, 1 atmosphere or its equivalent, 760 millimeters of mercury, 101.325 kPa. And this is basically just giving us a set of conditions that we can look at to compare gases to. And when we do have a gas at STP and we have 1 mole of that gas, because remember again, gases, molecules do not have individual volumes, the mole of any gas would be 22.4 liters. And we'll be using that towards the end of our unit, maybe using it a little bit with combined gas law and ideal. So that should get you through the last worksheet of this section for gas laws part 1 and 2. And we'll go over those in class shortly.